Welcome everyone. In this video we will derive the formula to find the volume of a sphere. So let me draw a sphere first. And of course it will be a bad drawing because I am drawing it on a 2D place basically. And I'm not going to get to do it in an artistic manner. I will only draw a circle, but think of this as a sphere, okay? So as I said, we want to calculate the volume of this. We want to derive a formula for this. Let's say the radius is r. And in fact, in a previous video, I did the derivation to find the volume of a sphere, but I used a method that was different than the one that I am about to show you guys. And if you want to see that other video, you can access it from the cards right now and also from the descriptions part. Now we're going to do the second method. And I don't think that any one of them is superior to one another, okay? They're just different ways of handling this problem. So today, in this one, we will do rotation to find the volume. And more specifically, we will have a coordinate plane. And the most convenient one, the most common one is XY plane. And then there will be a semicircle, like so. It will have a radius of r, and the semicircle, well, I don't know if you can say the semicircle is centered, but you guys get what I'm saying. This point is 0, 0. If we were to connect it to a full circle, that would be the center of the circle, and it is the origin. Okay? So we know this. And so, yes, how can we rotate this so that we get a sphere? If you did a little bit of volume calculations with integrals, you probably guessed what we're going to do. We're going to rotate this around the x-axis. And if you never did this kind of a calculation, don't worry, because this is the start of an incredible journey for you, and I am glad that I am the first person to show it to you. And so if this is the first time that you're seeing it, or if it has been a while since you did this kind of a thing, I mean, you need to just think of this in your head, or just you can get a piece of paper, cut a semicircle, and then rotate it to replicate the rotation that we are doing around the x-axis, and you will see that it forms a sphere. So as I said, we will rotate this shape around the x-axis. Now, a common mistake is to rotate a full circle. And if you were to do that, you would find double the volume, because even when you have the semicircle and you rotate it, you are able to form a sphere. You cover all of the parts that make up the sphere. So when you just add the lower part, you are basically counting twice. So please don't make that mistake. All right. So we're going to rotate it. But how does this help us? This helps us because we're going to think of it in this manner. So we're going to get a height like this. This is y, and we're going to rotate this disk. When we rotate this, semicircle, you can see that this part, it is going to form a disk, right? There will be a disk with radius y, and that disk will vary as we move along the x-axis, of course, and that is why we're going to in fact use integrals. So first of all, I want to say that the volume, the total volume, is going to be, we're going to have the integrals, and then we're going to be summing up all of these little disks. And let's draw an example disk. We have y here, and it is going to have a little thickness, which I drew exaggeratedly. Okay, this is exaggerated to make it look better. This is dx, right? The thickness is along the x-axis, so it is dx. I was about to say among. It isn't among, it is along the x-axis. Okay. And so yeah, we basically are going to sum up all these little disks so that we end up with the total volume of the sphere. And so it's going to be, well, we have... So hold on a second time. What is the volume of this guy? This is a cylinder, right? The disk is a cylinder. And the area, the base area is pi y squared, right? Pi r squared gives you the area of a circle, where r is the radius. Then you have the dx. So that is the little volume, the infinitesimal volume, and if we add up all of them using an integral, we get the full volume, which is the volume of a sphere. So that is the integrand, basically. Now, when you look at this, you should sense that we need to do something else, something more, because the integration variable is x, and the integrand has y in it. But how can we get rid of y squared? It is in fact not that hard. Because. Look at this. We know that to form a semicircle, we basically had x squared plus y squared equaling r squared, right? This is a formula for the circle centered at the origin. If we solve this for y squared, we're going to have r squared minus x squared. And we are only interested in the solution for this, where y is greater than or equal to 0. So for y squared, I will basically substitute r squared minus x squared. R squared minus x squared. Then we have the dx. Now the question is, what about the boundaries? What should the boundaries be? Because here it was kind of hard to write a boundary, because as I said, the integrand had y in it and the integration variable was x. Now that they are the same, it makes more sense to decide on the integration limits, boundaries of the integral. That's what I mean. And if you look at the picture here, the drawing, you can see that the x... Oh, by the way, we forgot the pi here, right? It was in front of the y squared, so let's put it. What was I saying? Yes, if you were to look at the drawing here, you can see that the x is going to range from negative r to positive r. So that's what I write here. And we can take the pi out of the integral, negative r squared minus x squared dx. Hold on a second. And if we were to take this integral now, let's take it. How do we take it? Well, it's going to be r squared x, right? R squared is a constant, minus x cubed over 3. And then we have the boundaries. Now we're just going to use the fundamental theorem of calculus. We are going to substitute the boundaries. It is r cubed minus r cubed over 3 minus r cubed, and then a minus r cubed over 3, so a plus r cubed over 3. And then I close it. So if I were to, well, let's see, what do we have? If we distribute this negative sign, we're going to have 2r, let's not change the color, we're going to have 2r cubed minus 2 over 3r cubed. And 2 is just 6 over 3, so it is basically 6 over 3 minus 2 over 3 is 4 over 3. So the volume turns out to be 4 over 3 pi r cubed. And this is probably familiar to you, as we use this very often, because calculating the volume of a sphere is very practical in lots of problems. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. And if you want to see further videos like this, please make sure to subscribe. I hope to see you in another video. Until then, take care.